Right. Hi, class. Now we're going to talk about oxidation numbers. So an oxidation number is what we call, is what we assume, according to this definition, is the charge of an atom in a molecule that we assume that all the bonds are ionic. So what we do is, for example, we have carbon dioxide as carbon, double bond O, double bond O. Now, in this, all these are covalently bonded. We know they all share electrons, but for our assumption, we're going to say what we're going to have is that these are actually ions. So this would be actually +4, and this would be 2 minus, and this over here would be 2 minus, and we have this attraction. This is what we're assuming. We know it doesn't occur. We know it's fake, but this helps us follow the electrons in a reaction, because what happens when we take, say, carbon methane plus O2, oxygen, and we're going to end up with CO2 plus 2H2O, and I'm going to put 2 there to balance this all out. And so what actually happens is that we've got to follow the electrons, how the electrons move in a reaction. Before we do that, we need to figure out how to assign oxidation numbers. I said, here's the rule for all the elements. So hydrogen. Hydrogen is the unique one out of this bunch. There's 3 oxidation numbers. It could be 0, 4, H2. -1, +1, if bound or bonded to a nonmetal. And that's on your periodic table. It's everything to the right of the metals. It is -1 if bonded to a metal. So, for example of this, if we have H2O, this is 2 hydrogens bound to an oxygen. These would be +1. We also could have NaH, which is sodium hydride. This sodium is positive, this would be negative. And all these are actually based on electronegativity. Alkali metals, always +1. Alkali earths, this is column 2, always +2. Noble gases, always 0. Now, I want to point out, in chemistry, we actually can react with some noble gases, and there'll be an exception to the rule. And that's the fun thing about chemistry, because it's getting all the exceptions. But always, always 0 for us. So these are the rules for this. And now for alkali metals, if the element only, and we say unbonded, it's going to be 0. The oxidation number is 0. Same thing, your alkali earths and everything else. And we take a look at the halogens. If we have like Cl2, the oxidation number that's going to be 0. Now, we're going to have some exceptions here. F is always, fluorine is always -1. Okay, now, here's the fun thing. Cl and all the other halogens and the rest, we're talking about I, Br, etc., -1 unless bound to oxygen. Now, the reason we say this is that oxygen has the second highest electronegativity. So if we have OCl minus, O's minus 2, Cl is going to be plus 1. Because oxygen is going to take the electrons away from chlorine, even though it's negatively charged. The negative charge comes from actually the oxygen, not the chlorine. This is the chemistry. So these electronegativities are going to be important when dealing with oxidation numbers. And so that's what we need to know. Now, column 16, chalcogen, oxygen. If it's an elemental, elements is always 0. If oxygen is either -1 or -2, usually -2, -1 if bound to itself. And what I mean by that is if we have HOOH, this is something called peroxide, these are actually -1. These are going to have a -1 charge. This is +1, this is +1, that evens it all out. This is called a peroxide. This is also very, very reactive. But 95% of the time, it's going to be -2. Only time it's positive if it's bound to fluorine. And we won't see that many. But you may, I can always throw one in it if you want. Picogens, nitrogen, ranges from -3 to +3, depending upon what's bound to it. What I mean, nitrogen is usually -3, +3. Sulfur can range from +3 or +6, depending upon what's bound to it. And the carbon family always, not sulfur, phosphorus. I'm sorry, phosphorus. Sulfur's under chalcogen. This is phosphorus. Carbon family, carbon is usually can go from -1 to +4. Silicon and below can be +2, +4. It depends what is bound to it. So these are kind of the trends that we see, but it's usually not with these two groups. With the chemistry, it usually varies. Something you need to be aware of. Now, transition metals, they're all the number. These vary depending upon the number, the valence shell, the electron configuration. Column 3 is usually, we have an S2D1 configuration. The charges are usually +1, +2, or +3. That's usually the oxidation numbers of anything in column 3. Anything, as you farther you go down, more you're going to have a little bit different because of the F orbitals that may be present. Column 4 is going to be an S2D2, usually +1, +2, +3, or +4. Usually the +2 and the +4 are more variable. With column 3 is +2, +3. Column 5 got an S2D3 situation, therefore it's going to be usually +2, +3, +4, +5. And again, these are all the oxidation numbers that could be present, and usually we're looking at +2 and a +5 as the main ones. So how are we going to figure out which one's which? So as you know, we go column 6 and we go 7 to 12, and it's all going to vary based on the electron configuration. So we're going to have it. Sometimes we can't know just by looking at it what we see. So how we determine oxidation numbers on a molecule is that you look at the sum of the oxidation numbers. It should be equal to the charge of the molecule. And if we don't know the element, or we know it's going to be variable, we're going to use algebra to determine the oxidation number, and we're going to give you a couple of examples of this. So here we have is K2CrO4. Potassium is in column 1. We know that's +1. Oxygen is always -2. But chromium we don't know. So and there's no charge to this, so it's neutral. So 2 times +1 plus that we don't know, plus 4 times a -2 is going to equal 0. We want to know what the oxidation number for chromium is. That's what we don't know. So 1 times 2 is 2, so 2 plus x, and so forth. That's going to be a -8. It's going to be equal 0. X, move the 8 over. 2 plus x is equal to 8. X is equal to 6, and that's the oxidation number of chromium is going to be 6. So when we're looking for oxidation numbers, potassium is going to equal +1 again. Oxygen is equal to -2, and Cr is going to be equal to +6. Now, I want to point out is that when we ask for oxidation numbers, we don't want the total number of oxidation states or the total number of oxidation numbers that we have for the whole thing, just for the element itself. So we've got 4 times -2 for -8. That's how this works. We're looking for the oxidation number of one atom of that element. And for this class, and we're just going to focus on the simple ones with not any fractions or anything like that. MnO2 got magnesium oxide, so we got 1. There's no charge to it, so Mn we don't know. Oxygen is -2, so X plus -2 times 2 is equal to 0. X is equal to X minus 4 is equal to 0. So X is equal to 4. So Mn, the oxidation number of manganese, is +4. Oxygen is going to be a -2. And that's how we work with these things. You'll have an assignment associated with this, and good luck.